Alrighty, everybody, welcome back. Let's continue from the first video. Let me share screen. Okay, here we are. So as you remember from last video, heat is a form of energy, and heat cannot be created or destroyed because even at cold temperature, we always have heat present. We can never get to 460 Fahrenheit, and we have latent heat, sensible heat. One we can measure, one we cannot. Sensible heat. As heat added or removed, temperature will change, easy peasy. Latent heat, a little bit more complicated, but we can go through it. Latent heat is hidden heat. As heat added or removed, temperature will not change. This graph shows the straight line up and down is the latent, the vertical line is latent heat, and this line is the sensible heat. Latent heat, sensible heat. So first we have ice, cold ice at negative 20 degrees. Add heat, add heat, add heat. That's sensible heat. Heat is increasing with the ice getting warmer and warmer until we hit 32 degrees. We start to melt. That's latent heat. We cannot measure it. Temperature will continue to be 32 degrees until we hit 33 degrees. Now we're in liquid form, 100% liquid. We add heat. Temperature increase. That's sensible heat up until we hit 212. And now it's back to what again? Latent heat, because 212 water continued to be 212 until it's gone, becomes gas or vapor, and gets hotter and hotter and hotter. This is important to know, superheat and subcooling, because it's a big part of refrigeration. Now, going back is the removal of heat, condensation, change of state, but no change of temperature. Then water will cool down until it hits freezing, 32 degrees. Again, change of state, no change of temperature. And then water will get colder as it freezes. And there's another chart looking at it. Another chart. Now, we have in the system, we have the compressor, the metering device, the condenser, and the evaporator. That's in your refrigeration system. The evaporator is the cold part of the system. Heat, the hot air enters the evaporator, and cool air out of it, or heat removed from the air. Evaporator's job is to remove the heat. I'm sorry, to absorb the heat is the evaporator job. The compressor's job has only one suction, one suck, compress, and discharge. That's the compressor's job. The metering device is the brain of the system. It regulates the flow of the refrigerant. Same as in California highways, the metering light regulates the flow of cars. And the condenser's job is to remove the heat remover. Now, the heat in the food in the refrigerator will enter the evaporator, and the heat outside will be removed from the condenser. Now, inside the evaporator, if you remember the video, we can also make the water boil at room temperature by removing the air around it. Right? So as the air moves out of as the air is gone around the water, it will cool down and boil. Because there's no air pushing down, it will cause all the water to go into vapor, oxygen, and hydrogen. And that's what's going on in the evaporator. Same thing when you make a wet rag and make it cold, will also drop down in temperature because it evaporates, because evaporation is a cooling effect. Now, the compressor is located outside, and the condenser is also outside because that will remove the heat. The evaporator is inside, either because that will absorb the heat. And there is the location of the metering device. There is many kind of metering device. We'll cover it into the metering device section. The metering device regulates the flow of the refrigerant. Now, in the system, we have the heat from the house enters the system, and the heat is rejected outside from to the air, to God. We are pretty much heating God. Package unit And this is also shown another picture, easy to see the heat from the occupied space enters and the hotter air out from the heat from the house being rejected outside and the heat from the system too. We'll cover that in heat pump. And there it is, your basic refrigeration system. The heat enters the evaporator and heat exits the condenser. Now we have a short video. I have it in the, you can watch it on your own. I have it there posted.
Name's Max. Check the microfarads. I store the charge.
So this about the capacitor.
I bring the torque. No rating.
Inside me. Heat leaves the air.
The evaporator.
Moves across my
Condenser.
fingers. Heat line.
Suction line.
Pressure. Low.
And compressor. Okay, let's move on. Okay, enough of this. Next slide. Alrighty, so this is the diamond I made. And system is off. Freon in liquid form. System on. The compressor will create a lower pressure. And the expansion valve feeds the evaporator. Freon begins to boil and reach its boiling point. And that's the latent heat. And Freon exits 100% back to the compressor. And that's when heat is being absorbed with the evaporator. And next, the compressor sucks, compress, and discharge high pressure vapor to the condenser. And now the condenser will reject the heat. The compressor comes on, Freon begins to condense and reaches condensing temperature. That's latent heat. And Freon becomes 100% liquid out. That's why I have different color codes. The light blue is vapor, low side. Red is vapor, high side. And orange is liquid, high side. Then in the expansion valve will expand. Freon 100% enters the pressure, expands the metering device, goes out 75 liquid, 25% vapor from the metering device to the evaporator. Then in the evaporator, liquid vapor mix 80-20, 75-25, not much difference. Freon boils and evaporates in the evaporator, 100% out back to the compressor. That's the diamond refrigeration cycle. Another way of looking at it, easy discharge line, hot gas on top, turns to liquid, subcooled liquid, goes to the metering device, expands, cold liquid up, vapor, 100% vapor, back up. Another way of looking at it. And also another way looking at it, all cool deal. You notice in the middle should be about 50-50 vapor liquid mix, 50-50 vapor liquid mix. Okay, now removing the heat, it's a little thing I wrote. Let's go through it. Temperature always goes from hot to cold. Path goes to the least resistance, always. 4 basic things we need to know. Heat travels from high to cool, high pressure moves to low pressure, high voltage to low voltage. That's also in my moving electron book. I will cover later. Now, HVAC, many forms of HVAC. We have HVAC is very big field, air conditioning, heat pump, refrigeration, ice machine, one section, piping and water, another part, refrigeration, compression cycle. That's what we're talking about right now, this section right here. We have also building automation. I don't know too much about that. I have very few experience with that. And electrical reading and schematic diagram is very important in this business. And of course, psychometrics, airflow, another part of HVAC, and the heating. A lot going on. My expertise is the refrigeration and ice machines. All right, let's move on. Heat. What is heat? Heat is a form of energy. Heat cannot be created or destroyed. Heat is present in deep space, even at -455. Heat added or removed does not change in temperature. Okay, temperature is measurement of heat and measured Fahrenheit Celsius. We have sensible heat, latent heat. Sensible heat, latent heat. Sensible heat causes change in temperature. Sensible heat can cause sense, you can feel it, sense when change temperature. Latent heat cause change in state, but no change in temperature. Latent means hidden in Latin. Latent heat is present when ice is freezing. Latent heat is present when ice is melting. Also, it's present when water is condensating, and when water is evaporating. That's when latent heat is present. And temperature does not change when latent heat is observed or removed. The heat is added, but temperature remains the same. Change in state, but no change in temperature is latent heat. Next, pressure. Pressure is the force that moves the refrigerant system in the system. Pressure travels from high to low. Pressure drops cause temperature to drop. Pressure rise causes temperature to rise. Pressure is increased by the compressor. Pressure is reduced by the metering device, which will cover the compressor in details when I do the compressor class. And of course, I'll cover the metering device in details. And pressure is measured by pressure per square inch gauge in refrigeration. And now remember always from high to low, and path goes to the least resistance in everything, especially electrical. Path goes in the least resistance and high to low temperature. Now pressure. That's a good example of how pressure goes high to low. When I went to Lake Tahoe, I got an empty bottle and sealed it at higher elevation. Empty plastic bottle sealed at 14,000 feet on the left, crushed by the air. As me and my wife driving back down to San Jose, then all of a sudden the bottle started getting crushed and crushed. Why? Because the air inside the plastic bottle is less pressure in it. Higher elevation, less pressure. Lower elevation, low pressure. Okay, makes sense. So this is a good example of and the lower we went, the bottle got crushed and crushed even more because the pressure at sea level is 14.696, while the pressure high elevation is less. Another example. Now I did it backward. This one now. This chips bag. This is actually this is in Lake Tahoe. You can see the back of Lake Tahoe right there. This is picnic table at Lake Tahoe, and the bag is. Why? Because this bag was made at sea level and sealed at sea level at 14.696 psia, but higher elevation is less pressure. So obviously the bag want to expand because pressure goes from high to low. Okay, heat flow. Heat travels also from hot to cold, always, okay? Right now the heat's moving into the glass. Right now the heat's moving into the house. Okay, and moving into the house because why the house 75 degree, outside 95. But if the house is hotter, if outside 55 degrees, the house is hotter, then heat will move out. Important, we don't cool, we remove heat. We are in the heat removal business and we have job security. Heat will always come back, will never go away. First law of thermodynamic. We're lucky, heat comes back. All right, we need something to increase the pressure and the temperature, and that's the compressor. We need something inside the house to absorb the heat. We need something outside to remove the heat, the condenser. So the evaporator must be colder, condenser must be hotter. And we need something to lower the pressure is the metering device. The compressor cycle. We need the evaporator inside the house to absorb the heat must be colder. The condenser outside to remove the heat must be hotter. The metering device to lower the pressure, and the compressor to increase the pressure. And here we are. There's the evaporator located on this chart and over here. And the heat is absorbed by the evaporator, and the heat absorbed by the evaporator, the transfer to the suction line. You can see suction line here is so big, 1, 2, 3, but in here is tiny because this is a diagram. This is actual. The diagram is never to scale. Okay, then the heat transfer suction line, compressor discharge line out, compressor to the discharge line, hot gas, and then the heat is through the suction line, the heat out discharge line from the compressor. And heat goes to the condenser and rejected out. Okay, and heat rejected by the condenser. Right now, evaporation. Evaporation is the change of any substance from liquid to vapor. Evaporation happens when we leave open cup of water in a room, it will evaporate slowly. Evaporation is surface phenomenon. Evaporation takes place at any temperature. Evaporation is a slow process. No bubbles are forming. No air pushing down the H and the O's will break apart and drop in temperature. Now the boiling point also means saturation temperature, evaporation temperature, also gauge temperature, evaporator temperature, or saturated temperature. All these are the same thing. HVAC have many terms. Some people say it's the saturation temperature. I don't like to use that word because it's located on the high side and the low side, makes it confusing. I like to use boiling point. There's only one boiling, and it's in the evaporator. Make it easy. It is the saturation temperature, correct. It is the evaporation temperature, correct. It is the gauge temperature, correct. It is the evaporator temperature, also correct. All these are correct. But I like to use boiling point, make more sense, easy peasy. Okay, condenser temperature, also condenser temperature, also gauge temperature, also saturation temperature. Let's just call it condensing temperature, easy peasy. And let's go back here. As you can see, it starts 75, 25 vapor, 50, 50, 100% out. And in here, 100% vapor and 100% liquid. That's now, there's another chart. Now we're going to go to the pressure enthalpy chart later. The compressor, vapor pump, pressure increaser, the heart of the system, vapor pump. Compressor between evaporator condenser. We have five kind, rotary, reciprocating, screw. I'll cover that in details when we do the compressor class. They all do the same thing, suck, compress, and discharge. Vapor refrigerant. Gotta remember, it's a vapor pump. People think a pump like a water pump. Vapor pump. We cannot have slugging. Compressor is a vapor pump. No liquid should ever enter slugging. We'll cover liquid slugging again in the evaporator and, of course, in the metering device and in the compressor. Slugging is very, very important in HVAC. We don't need that. I'll explain it again when we cover those topics. Let's move on now. Metering device, the brain of the system. Okay, and metering device, we have also 5 kinds: thermostatic, automatic, electronic, the cap tube, and the orifice. And we'll cover one by one when I do the expansion of the metering device section part of the class. Evaporator. Now, evaporator and flashing and evaporation. All right, here we go. So we start 80-20 vapor liquid mix, 75-25, whatever you want to look at it. And in the middle, it goes, the heat enters. Now the heat is being sucked into the evaporator, 50-50 now vapor liquid, and out 100% vapor to the compressor. And that's called superheated vapor. When a vapor is brought above, it is boiling point, it's superheated. Suction line temperature minus evaporation temperature is superheat. I'll cover that again later. And to measure superheat, we convert suction line temperature. We'll cover superheat later. De-superheat in the condenser, we have first de-superheat, 100% vapor. Then beginning of condensation, then 50% vapor, 100% liquid. End of condensation. Don't get too confused about de-superheat. I'll cover that again more in details when we do the condenser section class, whenever that will come up. Okay, and then 100% liquid to the metering device and back, circle and circle, we go. Circle and circle, we go. Alrighty, now let's move on. Temperature entropy diagram. In HVAC, we have a lot of diagrams, a lot of charts, which makes it so cool. That's why learning is so cool. So temperature entropy, it plots the thermodynamic state of the refrigerant. It shows us, yes, it shows us the temperature. This chart is important. It shows how the temperature change in the system. Okay. Superheat is the evaporator, subcooling in the condenser. Learning HVAC is super cool. Superheat, subcooling, we're going to go about the pressure, enthalpy, temperature, entropy. Now, the pressure enthalpy. Enthalpy is a fancy word for heat, okay? This line is the pressure, this line is enthalpy, heat added or heat removed. This is pressure, not temperature. The one on the right side, the one on the right side is temperature, on the left side is pressure. Now, Pressure, temperature, side by side. Vapor side is on the right side. Oh, backward. In the middle is liquid vapor mix. On the right side is the liquid side. And the condenser lives there. Evaporator lives there. Compressor and metering device are on those sides. And that's all four of them: high pressure, low pressure, liquid vapor mix. Now we start. We start with the, let's start here. This one starts with the expansion valve. Doesn't matter where we start now. Expansion valve is located here between the section in the yellow and on here on this diagram, and in actuality right there. Then we have the evaporator, next compressor, and condenser. Now, temperature enthalpy diagram. Between 1 and 2, we have superheated vapor, but be careful. Superheated vapor from the evaporator. We have two superheated vapor. This is superheated vapor from the evaporator, enters the compressor. And the compressor goes out. And we also have superheated vapor, but this is and superheated vapor temperature increase. But now this is superheated vapor from the compressor. Then we have compressor is big temperature increase. 3 to 4 is the condensation, is de-superheat, excuse me. 3 to 4 de-superheat, temperature decrease. And 4 to 5 is condensation, no change in temperature. And that's your latent heat. Then this is your subcooling, 5 to 6. 5 to 6 subcooling, temperature decrease. And expansion, 6 to 7. And evaporation, no change in temp. And it's called what? No change in temp? It's called latent heat. Okay, and back to number 1. Alrighty, now, temperature. This is the pressure now. Same thing, in the middle is liquid vapor mix. This is 100% liquid line, 100% vapor line, high pressure on this side, high pressure vapor this side, low pressure vapor this side, high pressure liquid, low pressure liquid. Superheated vapor from the evaporator. Superheated vapor from the evaporator. Low pressure vapor enters compressor. Superheated vapor from the compressor. High pressure vapor exit. 2 superheat. We have superheat from the evaporator and superheat from the compressor. Superheat, compression superheat. Now, de-superheat between, and we'll cover that in the condenser section. Then beginning of condensation, end of condensation, subcooling, expansion, low pressure, beginning of evaporator, low pressure mix. We can say that this is the beginning of the boiling point, and then end of the evaporation. So we have boiling point, evaporation, end of evaporation, superheated vapor, back to the compressor, back to number 1. Alrighty, beginning of the evaporator, end of the evaporator, start of the compressor, end of the compressor, beginning condenser, end of condenser, expansion device. I misspelled expansion, cool. And this is your subcooling. Let's go back here, and that's your superheat. I'll cover it again later. And always pressure from high to low, temperature from high to low, path goes to least resistance. We need the evaporator inside the house to absorb the heat, condenser outside to remove the heat, metering device to lower the pressure, lower temperature, and compressor to increase the pressure and increase temperature. As easy as 1, 2, 3, as simple as A, B, C. The heat absorbed by the evaporator, the heat transfer suction line, the heat transfers discharge line, the heat rejected by the condenser. And then we are here. I'm going to bring this apart. Inside the house, 75 degrees. Evaporator must be colder. So guess what? 35 evaporator. So the heat can enter it. And outside temperature 95, condenser must be hotter at 115 or 120. So we can remove the heat. And let's put it together here, step by step, one by one. Any copy you of anything, let me know. I'll send you, email you copies. Now, easy to remember. Superman is up there. Superheat is in the suction line minus boiling. Superheat is suction line minus boiling point. Superman is in the air vapor. Superheat is in the vapor side. Easy to remember. Thank you, Mr. Eugene, for bringing up that idea in his book. And also boiling point, also saturation temperature, evaporation temperature, evaporator temperature, or gauge temperature, or saturation temperature also. Okay, and LP, that's the what this means. And subcooling. Subcooling is in the high side and in liquid form, submarine in the water, subcooling in liquid, easy to remember. Submarine is in liquid. Subcooling is liquid, subcooled liquid, superheated vapor. Thank you, Mr. Eugene. Okay, but let's move on. Put this together, superheat, subcooling. Superheat, subcooling, the only one cool is the teacher, is super cool. And learning HVAC is super cool. All right, so superheat, subcooling. First thing we do is we convert high pressure to temperature, and we get our condensing temperature. Then we measure liquid line temperature. Okay, then we subtract liquid line temperature minus condensing temperature equals subcooling. And usually 10 to 20. Next, superheat. We convert low pressure to temperature, and we get the boiling point. Then we measure suction line temperature and the boiling point, and we get the superheat. Should be 8 to 12. Another way of looking at it, this is a chart to do it one by one. All right. First, we look at the pressure, low pressure, high pressure. Using a PT chart, we convert to temperature. And we write here our temperature. Low pressure, whatever it is, boiling point, whatever it is. High pressure, whatever it is, condensing temperature, write it here. Boiling point, condensing temperature. Next, using a thermometer, that's easy part. Measure suction line, measure liquid line, and write it down. Suction line, liquid line. Then we do subtraction. Suction line minus boiling point, superheat, and condensing temperature minus liquid line, subcooling. Then this is a chart I made. It gets more complicated as we move on because we have three different things: high temp, medium temp, and low temp. High temp is air conditioning, medium temp refrigeration, and low temp is freezers. And then so the boiling point changes, of course. In air conditioning, boiling point usually should be about 35. In refrigeration, 15 to 20. In low temp, boiling point should be about 0, maybe minus 10, even negative 10. So the boiling point affects the temperature of the occupied space. And then also the high side, of course, depends on the outside air, but also we have two kind of condensers, standard condenser or high efficiency condenser. We'll cover that later. And then we have different kind of expansion device and different ways to charging, depends on the expansion device. And then we measure the air out and air in, and we do the electrical reading. So this is more advanced, and we'll cover it more later. Okay, this is it for now. Thank you. Any questions, leave in, call me. Thanks.